This is the third and final section of Chapter 8 on numericals methods, and this is all about Simpson's rule. Now in Pure 2, the Pure 2 book, you would have learned about a numerical method called the trapezium rule. I'll put a link to it in the description. And the trapezium rule is a way of estimating the area under a curve by dividing the area up into strips. Okay, so this is a form of numerical integration. So I'll just write here numerical integration, and integration in that we're trying to find the area or estimate the area under a curve. So it's about estimating area under a curve. Okay, so let's draw one here, just a random curve. And with the trapezium rule, what we're doing, as I said, is if I've got some sort of curve, it goes like this, I divide it up into equal strips. So let's say I want to find the area between here, A and B. Let's call this area, or this limit here, B. And each of the strips is divided up into is actually a trapezium. So we straighten up the top of the edges here. We work out the area of each of these strips. Okay, if this were the graph of, let's say y equals f of x, get rid of that, y equals f of x, then the area under the curve of f of x is approximately like the area or the total area of these trapezium, these strips, total area of these strips. And here you can see I've divided up into 4 strips. Now it's okay, but we can lose some accuracy. If you look here, you can see the curve, the graph curves upwards, so my trapezium lays underneath the curve. Here it looks like it's a bit over the curve. Here these don't seem too bad. We can lose some accuracy with the trapezium rule in that we can easily overestimate or underestimate depending on the function that we have. So we have another way of doing this numerical integration, estimating the area under the curve, and that's using Simpson's rule. Now the main difference between the trapezium rule and Simpson's rule is that these bits at the top here, which we made into straight lines so that we could get these trapeziums here, in this case 4 trapeziums, we round them off. And in fact what we do is we pair up these bars, each of these strips, and then we draw a curve or quadratic that passes through those 3 points. So let's sort of write down the main point. So Simpson's rule. Okay, so first thing is that bars or strips, let's call them strips, strips are paired up. When the strips are paired up, then we the top of the pairs of strips has a quadratic curve joining them up. So let's try and zoom into one and I'll show you what that might look like. Okay, so let's draw a graph that goes like this, for example, and we've got our strips here like this. Now with Simpson's rule we need an even number of strips because we're going to pair them up. So here it looks like I've got 2 pairs of strips. So I've got this pair here and I've got this pair here. And then what we do, rather than join the tops with straight lines, I'll try and draw this, we work out a quadratic curve that passes through those 3 points. So something like that, a quadratic curve passing through those points. And then the same here, a quadratic curve passing through those points, those 3 points. Okay, and you can see that it's a better estimate, yeah? So this will give a better estimate to the area than using the trapezium rule. Now the advantage with the trapezium rule is that the formula for the trapezium rule is in the formula booklet, but with Simpson's rule is not in the formula booklet, so we need to remember it. Now I'm going to write out the full form and then straight after that write down an easier form to remember. Right, so here you can see like the full form of Simpson's rule, and you can see, well, it may be difficult to remember. So first of all, let's just write down what these values are. So y0 is the height of this bar, y1, y2. So this is just the height, basically either side, not the bars, but either side of the strips. And you'll notice, well, basically the height of the first strip, or one side of the strip, is here. This is the very last value, so in this case it would be y4, and then you've got 4 times all of these even y values plus 2 times all of these odd y values. Now what this gives us is a much more straightforward way to remember Simpson's rule, and it's this. If I want to estimate the area under a curve, then this is an easy way of remembering it. So third h, I should remember mentioned h. H is the width of each of these. Yeah, each one of these bars here has a width of h. So 1/3 h times by, and this is going to make it easier to remember. So here we've got like the endpoints, the first and the last value. So we want the sum of those endpoints, so endpoints, then plus 4 times all of these y values here, so like y1, y3. That's what I'm going to call the odd values. So the y value here, the y value here. So 4 times odd values plus 2 times the even values. So this just gives an easier way of remembering Simpson's rule. As I said, it is not in the formula book, but if we can remember that, then we are able to apply it. And if we remember that and use this form, it's easier to remember and it's easier to use. Okay, so here it says use Simpson's rule with 4 intervals to estimate this area between 0 and 2. So first thing we'll do is we'll write down what Simpson's rule is. So this area under the curve is approximately 1/3 h. Then we want to add the endpoints plus 4 times the odd values plus 2 times the even values. So let's put a times sign rather than that looks like a minus. 4 times even values. Right, now this is where a sketch might be useful. Now it says 4 intervals. Now you may be tempted just to work out 4 values, but what does 4 intervals look like? You could think of 4 intervals like 4 strips. So if I just draw a random graph there, if I want 4 intervals, I want 4 strips. So that's 1 strip, 2 strips, 3 strips, 4 strips. This is what the question is asking for, 4 intervals, 1, 2, 3, 4. Can you see that I need to work out actually 5 y values? Actually, let's write those as the heights rather than they look like the actual x values. So y0, y1, y2, y3, y4. So basically the number of strips or intervals plus 1 gives the number of y values we need to work out. So number of y values, and actually the number of y values, because we're going to do this in a table, is the number of columns that are going to be in our table. So I always do these questions with a table. So the first part of the table is going to be our x values. Now, because I'm integrating or doing numerical integration from 0 to 2, I will put 0 here for x. I'll work out all my y's in a moment. I need to know how much to go up by. Now I know that I'm integrating, I know this is not accurate, but this is meant to be 0 and 2 here. So let's just move my axis to there, like that. So that will be y, this will be x. Still the same number of strips. So if I'm going from 0 to 2 and I'm dividing 2 up into 4 bits, then 2 divided by 4, 0.5 or a half. So that means that x must go up by 0.5. So I can fill in the top row of the table. So 0, 0.5, 1, 1.5, and 2. So you can see 5 values, even though there are only 4 strips. Number of values, 1 more than the number of strips. Okay, so we will use the formula once we have worked out the y values. Now, how do we work out the y values? Well, we just use what we've been given here. Okay, so each y value is going to be equal to e to the minus x squared plus cos x plus 1. Now the easiest way to do this, rather than work out each one individually, is on your calculator we're going to turn it into a table. So if you press menu and table is 9, so if you've got a ClassWiz calculator, let's write it down here. So menu and then 9. 9 is the one that's for a table. We'll do that. Then it says f of x. So once it says f of x, in this case, we are going to type in this. So I will type in e to the minus x squared plus cos x plus 1. Once I've typed in my function, and there is an X button, by the way, that you can use. There's a button that's got X on it. That makes it easier to type it in. And the X is underneath the on button. So we use that for X. And then you can just press equals once that function is typed in. Make sure we're in radians as well, because we've got some trigonometry here. And anytime we do calculus, integration or differentiation, we need to be in radians. Then it will come up g of x. Well, we're not typing in the second function, so we can just press equals straight away, straight after that, because we don't want to type in a second function now. For the start value, I just type in 0. This is where my table starts. Then it says an end value. Well, my end value, I'll just type in as 2 because that's the last value in the table. And the step, well, that's how much I go up in. And my step is going up by 0.5 So I'll just type in 0.5. Press equals again, and the table appears. The table goes downwards rather than sideways, but that's not a problem. And I just fill in the values. So I can see next to where x is 0, it says 3, so I put 3 down. Then next to 0.5, it says 2.6563. Underneath, next to 1, 1.9081, 1.5, 1.1761, and I need to scroll down so I can at least see the last value next to 2, 0.6021. Okay, so now we can work out the approximate area. So the approximate area, remember, is going to be 1/3 times h. So let's write down the area is approximately 1/3 times by h. H is 0.5. That's the width of each of these bars. Times by, so what do we want now? The endpoints. So the endpoints are 3 and 0.6021. Then plus 4 times the odd values. So let's just write down what values these are. y0, y1, y2, y3, y4. So the odd values, those are y1, which is 2.6563, and y3, which is 1.1761. Remember, you always start with y0, not y1. Then plus 2 times the even values. Now the even values, let's just get this out of the way here. Those are y2 and, well, not y4 because that's the last one, so we don't include that one. So just y2. So maybe if I wrote down here, this one and this one is the end. Here's my odd. So the only even one is this. So make sure you don't add in y4 as well, because we've already accounted for that. So that'll be 2 times 1.9081. So let's work that out and see what we get. So changing it back to calculator mode, menu 1, I get this 1317. That's the full thing that I get on my calculator display. We'll give it to a suitable degree of accuracy. The question doesn't say. I would do a minimum of 2 decimal places, or even just look at the number and say, right, I suppose, if I wrote 3.79, that would be fine because there's a 1 that comes after it. Or I could even go up to 3.7913 because a 1 comes after it. So maybe I'm looking at a value that I can write down without rounding. So final answer, my estimate for this area, just write it down, plus cos x plus 1 dx is approximately 3.7913. Okay, and that I've done it to 4 dp. So minimum of 3 significance figures, 4 decimal places is fine, because I've written all of these values here to 4 decimal places. So 4 decimal places, any more than that wouldn't really be accurate because I haven't written these values to more than 4 decimal places. So this really is the maximum level of accuracy that I can write it to. Yeah. Right, you should now be able to do exercise 8C on pages 174 to 175. Recap. So Simpson's rule, we can write simply. We'll do it in its simplest form because this is the form we want to remember, is going to be 1/3 h. So remember, h is the width of the strip, Remember with Simpson's rule, these strips are paired up. Then we want to add together our endpoints, plus 4 times by the odd values. So these are going to be y1 plus y3 plus y5 plus and so on, plus 2 times the even values. So that's going to be y2 plus y4 and so on. And my endpoints, well, that's going to be y0 plus whatever my last value is. So we'll call that y2n. And this will give us the approximate area. Now, sometimes in these questions, it may be something that you can integrate and you can work out the exact area. So you may be asked to work out the percentage error. And this is something that students often forget. So the percentage error is the error divided by the exact value. So the error is going to be the difference between the exact and your estimate, between exact and estimate. And once we've divided it by the exact value, we times by 100 to give us the percentage error. So I'll just put that there just in case you've forgotten how to do that.